Hey guys, welcome to video 38. Today we're going to talk about Darlington and Sziklai pair transistors. We're going to look at an overdrive or preamp circuit that's based on the Sziklai pair. We're going to examine a complete power amplifier, and we're going to look at power switching using a stereo quarter-inch phone jack. All right, let's start with the Darlington. Over here on the left side of the screen, we've got an NPN Darlington transistor. It's made by cascading two regular NPN transistors, as we have shown, but we treat it as a single three-terminal device with a collector, base, and emitter. All right, let's figure out what the overall beta of this transistor is. Okay, so starting with the base current, we can see that the emitter of Q1 is going to have a current that's about beta times larger. That supplies the base of Q2, so Q2's collector current is beta squared times the original base current. We're assuming that beta for Q1 equals beta for Q2. That allows us to write beta squared, which makes the algebra a little bit nicer later on. All right, now if we assume that we've biased up the transistor and we've got an ICQ, this is the small signal model we're going to use to represent the Darlington. All right, and what I want to do here is derive an equation for Rin looking into the base from a small signal perspective. All right, so let's start by looking at little re2. We know that little re2 is approximately equal to V sub t, the thermal voltage, divided by ICQ. All right, now little re1 similarly is approximately equal to V sub t over IC1, but IC1 is also ICQ divided by beta, so let's make that substitution, and that gives us beta times Vt over ICQ. And notice that V sub t over ICQ is little re2, so finally we can write little re1 as beta times little re2. All right, now looking into the base of Q1, here's what we're going to see. Rin to the base is equal to beta times little re1, but that's the same as beta times little re2, plus what we see down here, which is also beta times little re2. So we can simplify this, and what we get is 2 beta squared times little re2. Now, for the sake of simplicity and writing convenience, let's just say that little re overall for the Darlington is the same thing as little re2. So finally, we get the equation for Rin to the base is 2 beta squared times little re. All right, and as usual, I've wrote these equations in a nice form over here for you guys. So let me drag that over, and you'll have something nice to look at. So here we go, and there we are. And as another popular electronics YouTuber would say, and Bob's your uncle. Okay, so there we are. Now, let's derive a voltage gain equation for this transistor, assuming we're using it as a Class A common emitter amplifier. Okay, when we do that, we're going to have an external R'B, that's the AC equivalent of the base biasing network, and we've got R'C, which is the AC equivalent of the load resistor and collector resistor. Here I have no external emitter resistor. We're assuming it's fully bypassed, but we can add that in later. Okay, so let's start by determining the base current. Okay, and that would be given by, whoops, let's get the pencil active. I sub b equals V in divided by Rin to the base. And we know the input resistance looking into the base is 2 beta squared Re, so it's V in divided by 2 beta squared times little re. All right, now let's look at our output voltage, okay? The output voltage is negative IC times R'C. V out equals negative IC times R'C. All right, and remember, I sub C is, for a normal transistor, beta times IB, but for a Darlington, it's beta squared times IB. So if we substitute beta squared times IB for I sub C, we get V out equals negative V in times beta squared times R prime C divided by 2 beta squared times little re. And the beta squareds cancel out. We get negative V in times R prime C divided by 2 times little re. And finally, voltage gain is V out divided by V in. So if we divide out the V in, we get AV equals negative R prime C divided by 2 times little re. So there is the voltage gain for the Darlington in a Class A common emitter amplifier with a bypassed emitter. Right? It's very similar to the equation we got for a single transistor, except we have to double little re in the denominator. So what we're doing here is trading off half of our potential voltage gain in order to get really high input resistance. And that's usually a pretty good trade-off. But there are some other negatives that come along with the Darlington. We'll see them soon enough. But let me bring over the nice version of these equations for you again, and give you a nice reference that you can use for future reference. And I might use this in a book in the future too, so that's nice too. Anyway, there's our equation. Now, what if we did add an emitter resistor here external? We'd normally call that R prime E, right? If we added that in, all we do is add it to the denominator, but we don't multiply it by 2. Now, I'm not going to go through the whole derivation. We've seen enough algebra. I'm just going to write the equation here that if we have R prime E that's not equal to 0, then our voltage gain is going to be equal to negative R prime C divided by 2 times little re plus the external R prime E. Okay, so it's a very simple modification, but we don't multiply it by 2. All right, now let's put all this to use by analyzing a real amplifier circuit. Okay, so here we have a Darlington Class A common emitter, and if we just take a glance at the circuit, the first thing you might notice other than the Darlington is that our biasing resistors are pretty high in value compared to what we've been seeing. And that's because the input resistance to the Darlington is so extremely high. If we look into the base from a DC biasing perspective, we're going to see beta squared times Re. So that's 5,000 times 1,000. Looking into the base, we see an effective resistance of 5 million ohms as far as DC biasing goes. And remember, for a stable Q point, what we want is beta, or beta squared times Re, to be very large compared to RTH. 5 million is very, very large compared to 52 k ohms, so this is going to have a very, very stable Q point. All right, now let's look at the values I have calculated over here. All right, ICQ 2.1 milliamps, VCE of 6 volts, and it's nothing too interesting until we get down here to Rin to the base. All right, now this is the small signal input resistance looking into the base, and since it's fully bypassed, that's going to be beta squared 5,000 times little re. 5,000 times 12.4 is 124,000 ohms. Very high input resistance to the base. Now when we factor that in with RTH, we get an overall input resistance of 37 k ohms, which is not bad. Our voltage gain works out to be negative 52, decent. Our current gain is negative 962, which is very good compared to other amplifiers we've seen. It's always going to be less than 5,000. And our power gain is 50,000. That's very good as well. And all these large signal values, IC SAT, VCE cutoff, VO max, and min, these are computed the same way we did for any other Class A amplifier. So if you want to look back at a previous video to find this stuff, it's shown back there, and we've done it many times. All right, now let's look at a Darlington Class AB push-pull amplifier. All right, in this case, I've constructed Darlingtons using a 2N3904 and a tip 41. So this is actually a high power Darlington. And over here we've got a 2N3906 with a tip 42. So that's a PNP power Darlington as well. We don't need a big transistor for the input side because this transistor carries much less current than the output side. This Q2 is doing all the work for this Darlington, and Q4 is doing all the work for this one. All right, now notice we need 4 diodes to overcome these 4 barrier potentials and eliminate crossover distortion. This looks kind of like a current mirror situation, but it's not, okay? There's really no simple relationship between ICQ and I1, and that's because even if we tried to set up a current mirror, Q1 and Q2 are operating at drastically different collector currents, so these diodes are operating at the same current through each one. We can't match them up to these transistors. It just doesn't work. So what we have to do here is kind of empirically figure out what R1 and R2 values work well for our transistor pairs and the diodes we're using. Okay, there are a lot of variables here, so you have to experiment with it a little bit. And I've just shown these as pretty high value resistors just to be on the safe side that we don't get a super high ICQ here. All right, so there are other biasing arrangements where we don't have to use so many diodes. There's a thing called a VBE multiplier that we could use here, but as I've said many times before, that's a topic for another day. Okay, but anyway, I think you get the idea how this is going to work. It's a pretty common circuit. One thing we have to watch for is that these transistors tend to oscillate. All right, so when we power this up, you might see an output signal that's in the megahertz range, and that's because these transistors are oscillating. So you've got to be really careful about your wiring and supply bypassing. Okay, I'm going to talk more about that later. So for right now, suppose we didn't want to actually construct our own Darlingtons out of discrete transistors. What we could do is use something like a tip 120 and 125 or similar, and these are monolithic Darlington transistors in a single TO220 package. All right, if we look at it, they're designed for general purpose amplifier and low speed switching applications. All right, this kind of points out another disadvantage of Darlingtons, and that is they have terrible high frequency performance. Okay, just probably 10 times worse than an equivalent normal NPN transistor or PNP transistor. They're very slow switching, and that's why the manufacturers integrate in these resistors in parallel with the base emitter junctions. These are designed to speed up the switching speed of these transistors. They're really not too helpful from a small signal amplifier perspective, but they do help in switching applications. Now, this transistor has a typical beta of about 2500 with a collector current of 4 amps. And, there's not a whole lot else to say about it. VCE SAT is a little bit on the high side, 2 volts at 3 amps, 4 volts at 5 amps. But anyway, these are the kind of transistors you'll probably see out in the wild. And if you didn't want to use them, you could build your own. All right, now let's go and talk about the Sziklai pair. All right, so what we've got here at the left-hand side is an NPN equivalent Sziklai, and down here is a PNP equivalent. Notice they're built out of a mixture of NPN and PNP transistors. The input transistor determines the overall type of transistor it is. This is an NPN, this is a PNP. All right, it's pretty easy to see what the current gain or beta of these transistors is. If we've got an IB flowing into Q1, we get beta times that in its collector, and that forms the base current for Q2. So the overall collector current is beta squared times IB, just like it is for a Darlington. So generally, we're going to assume that beta squared is about 5,000 for the average Sziklai transistor as well. Now over here I have an amplifier. It's an overdrive or a preamplifier that's based on a Sziklai, and it's going to have some pretty impressive numbers associated with it, but let's take a look at what we've got. Okay, first of all, we got relatively high biasing resistor values. Okay, again, that's because the input resistance to this transistor is very, very high. We've got a VTH of 1.54 volts, and RTH is 46.4K. And when we do the analysis on this circuit, here are the numbers that we come up with. Okay, we get about 1 milliamp ICQ, 3.5 volts for VCEQ, and as we go down through the list of values, nothing's too interesting until we hit R into the base. That's 130,000. It's very high. Overall input resistance is R into the base in parallel with RTH, and that's about 34K. We've got really high voltage gain, negative 123. Current gain is negative 1,300. That's impressive. And finally, the power gain works out to be 160,000 for this amplifier. That's really good. All right, now all of the large signal quantities, there's nothing different there. We've computed these for other amplifiers. We use the same techniques. Now, I actually built this circuit, and the measured values I got are here in red. Now, first of all, my battery was actually 9.5 volts instead of 9, and I got an ICQ of 1.27 milliamps, which gave me a lower VCEQ of 2.5 volts. The voltage gain actually worked out to be about negative 130, better than what we predicted. And my signal limits, VO max, not too bad, but VO min is off a bit. All right, now one thing, again, that could account for this is that my battery's a little higher terminal voltage than expected. But one of the main culprits in getting these different measured values is related to Q1. All right, consider that we biased this transistor up for about 1 milliamp ICQ, and that's flowing through Q2. Q1 is carrying a collector current that's about 100 times lower. So with 1 milliamp ICQ here, we're going to get about 10 microamps for ICQ1. All right, it doesn't take 0.7 volts to bias up this transistor for a 10 microamp collector current. It really takes maybe about 0.5 volts. So here's a tip when you're using Sziklai transistors. Let's not assume that our VBE is 0.7 volts. Let's assume that VBE is maybe about closer to 0.5 volts for the Sziklai in a typical Class A small signal amplifier application. And the reason is because Q1 is running at a very, very low collector current. We're going to have a lower VBE to produce that current. 0.5 volts is a good estimate, and I recommend that you go through this analysis using 0.5 volts as the barrier potential and see if your calculated values come out close to the measured values. I think you'll be surprised at how good the approximation is. All right, now, since I built this amplifier, I figured I might as well do some scope captures as well. All right, so first here, I overdrove the amplifier to find my clipping points, okay? And we can see the cursor's located at 3.6 volts on the positive peak and negative 2.32 volts on the negative peak. All right, so that's where I got my experimental clipping points from. Then I adjusted the amplifier so that I got about 3 volts peak to peak out. And this is the display I got. It looks like a pretty clean sine wave, okay? But I figured I would test that out by doing an FFT, that is a fast Fourier transform on this signal. The Fourier transform tells us the signal spectra for a given waveform, and if this was a pure sine wave, it would just consist of one peak. All right, and that's pretty much what we've got down here. It's hard to read, but this is set for 200 millivolts RMS per division, so we've got 2, 4, 6, 8, 1 volt RMS, and the frequency is 250 hertz per division. So here's 250, 500, 750, 1 kilohertz. So we've got this spike at 1 kilohertz, and it's got an amplitude of 1 volt RMS. Now the correlation here is that if we look at this signal, it's about 3 volts peak to peak, so that's 1.5 volts peak, and the RMS value of a sine wave is 0.707 times the peak value. 0.707 times 1.5 is 1 volt RMS. So we have a 1 volt RMS sine wave, and we get a 1 volt RMS peak down here. Now, it's not quite a perfect sine wave because when we look at the frequency spectrum, we see we get this little blip over here at 2 kilohertz. So, you know, it's not perfect, but it's not that bad either. All right, so that's just an example of some of the things you can do to check the operation of an amplifier. And most modern digital sampling scopes have spectrum analysis or FFT capability. And we'll talk more about this stuff in future videos as well, okay? So you've got a lot of cool stuff to look forward to. All right, now let's take a look at this power switching setup we've got, okay? I'm using the input jack to control whether the amplifier is powered up or not. So when there's no jack in the, or plug in the jack, the ring and the sleeve are separated and the 9-volt battery has no path to ground. When we insert a mono plug into a stereo jack, what happens is the sleeve of the mono jack shorts the ring connection to the sleeve, and it completes the circuit, so the battery has now a connection to ground and we can run our amplifier. You have to use a mono plug with the stereo jack to do this power switching. A stereo plug has a separate ring and sleeve, so it won't make the connection. All right, but that's a pretty common technique used in stomp boxes and other effect boxes for you know, guitar applications. All right, now let's take a look at a Sziklai power amplifier. Okay, so what we've got here is a complete amplifier. The output section is based on Sziklai transistors with a few minor modifications. And let's start there, looking at the NPN side. We've got a 2N3904 and either a TIP 42 or an MJ2955 power transistor. All right, now notice that I've added a small capacitor from the collector of Q1 to its base. As I pointed out earlier with Darlingtons, these transistors also have a tendency to break into oscillation, especially when you're using them as emitter followers. So what C2 does here is causes the gain of Q1 to roll off at a lower frequency than the typical oscillation frequency of this type of arrangement. You could get an oscillation frequency anywhere from the megahertz range up to the hundreds of megahertz. All right, so Q1 causes the beta of, or I'm sorry, C2 causes the beta of Q1 to roll off well before we hit those unstable frequencies up in the megahertz range. Same thing down here with Q3. All right, now I've also included a 100 ohm resistor in series with this emitter and this emitter as well. These are emitter swamping resistors. The function of these resistors, well, it's twofold. First of all, because I don't have matched diodes with these transistors, there's a chance that I could get more current flow than I'd like. So R8 and R9 help to reduce the chance of overbiasing the output transistors. Okay, and they also contribute to making this thing more temperature stable as well. If these transistors warm up at a different rate than the diodes, it could cause problems. So R8 and R9 provide some negative feedback and stabilize the output in terms of temperature. I've had my students build this amplifier dozens of times, and it always works great. So this is really a nice design. If you feel like throwing an amplifier together, it's pretty good. R6 and R7, 10K ohms seems to work very well for those. And you know, we've got a pretty decent amount of output power depending on what the supply voltages are. Now, over here to the left, I've used a dual op amp as the driver for this output stage. A number of different op amps are listed. You could use any of these. The LM358 is probably the least high performance of all of them, but it's also the least likely to cause oscillation too, so it's not really a bad choice. All right, we have each of these stages set up for a gain of 11. So we've got a gain of 11 for op amp U1A, gain of 11 for U1B. So overall, we're going to get a gain of about 100, factoring in the output stage gain being less than 1. All right, I've used a coupling capacitor on the input just on the off chance that you might have a source with a little bit of DC offset. We don't want that to cause a DC current to flow through our loudspeaker, so the coupling capacitor helps prevent that. We can use power supply voltages ranging from plus or minus 10 volts to plus or minus 18, and the maximum power output changes accordingly. And I've even used it with as low as plus and minus 5 volts, but you don't get much power out there, so I wouldn't recommend that. All right, now as I've said, I've had my students build this lots of times in the lab, and I've built it myself, and here's a version that I threw together recently, well, maybe a few years ago. But in any case, this is a stereo version of that amplifier. We've basically got 2 power supplies and 2 amplifiers, and I used point-to-point wiring on proto boards here on perf board with 2 separate op amps instead of a dual op amp, but it really doesn't make any difference. That's what my layout looked like. Here's the box with heat sinks and transistors mounted on each side and a nice little power indicator. All right, now I just set this up and did some tests today, and with an output of 500 millivolts peak to peak, which is pretty small. If we look at the waveform, there are really no hints of crossover distortion at all, so our biasing arrangement is working very well to eliminate the crossover distortion. It's usually worst on small outputs, okay? So that would be where it's most noticeable. Then I turned the amplifier up and drove it into clipping, and we got a maximum output of about 26 volts peak to peak. That's with a 30 volt plus and minus 15 volt power supply on each amplifier. So we're getting about 26 volts peak to peak right at the verge of clipping. And when I do the calculations into a 10 ohm load, that's a power output of about 8.5 watts per channel. Not too bad. All right, and speaking of the output, I didn't want to connect a speaker across the output when I'm doing the testing because I would like to keep my hearing intact. So I just use power resistors as the loads. Here I have 10 ohm resistors, and I can't stress enough that when you're testing power amplifiers, you always need to have a load connected to the output. Never run a power amplifier with no load connected to it. That's a really good way to destroy your amplifier. So when you're doing testing, if you don't want to use a loudspeaker, which is probably a good idea, connect a power resistor that's about the same resistance as your loudspeaker across the terminals. I used 10 ohms, but 8 ohms or 12 ohms would probably work just as well. We'd get different power output levels, but you just have to use some kind of load on your amplifier. All right, so that concludes today's excursion into the land of Darlingtons and Sziklai pairs. All right. Next video, I think we may talk a little bit about field effect transistors. Don't hold me to that, though, because I might change my mind. And okay, guys, I will see you all in the next video.